rotating. So deformation profile also you note it here. This is the rotation value, and here this condition you can see this is a fixed simulation. If you have fixed beam, if you apply the load here, fixed is all degrees of freedom is fixed, that means snap, just like cemented into the wall kind of thing. And the deflection pattern, if you see for this one, it starts with 0 and rotation also it is 0, the slope, and then it starts deflecting like this, right? So you can see the deflection pattern this and this is there is a significant difference. And here we can see the cantilever beam. It has the deflection delta max. This is the pattern of deflection, and deflection scale is almost 8 times. And simply supported beam deflection is like this, and fixed beam is deflection is like this. Here mainly we have to see the simply supported beam. The stress for this condition, let us see this one case importance of boundary condition, simply supported beam and fixed beam. We are applying 30,000 Newton with the cross section of this beam is 100 mm, say, and this example is create 3 nodes, 1, 2, 3 nodes, and 2 beam elements. This is one beam element, the second beam element. Apply the force at the central node like this, and appropriate boundary conditions at nodes. You just keep it one condition like a simple supported case, for example, and solve one comparative results. If applied boundary conditions are correct, the results would match the following value. For example, delta is 1 by 48 PL by EI, and the bending stress is M by Y, M star Y by I, M is PL by 4. This is one condition. Other one is in case your results are not matching with above values, and try the following formula: 2 by 384 PL by EI and sigma M by A, M is PL by 8. If your answer matches with the second set of formula, then it means fixed boundary conditions have been applied instead of simply supported. You understand, right? That is almost the moment values also it's varying PL by 4 to PL by 8, and deflection also it's 1 by 48 to 2 by 384. So there is a variation in the deflection as well as the stress. That variation you can see here. In case of fixed, it's only 38, half of the stress. In case of simple supported, the stress is 76. The same way here, deflection is 0.64 in case of simple supported, but in case of fixed, it's just 0.16. So difference between the two boundary conditions is just because 1 degrees of freedom, that is rotation about the z axis, that we have seen right here. This rotation about z axis. That is free in case of simple supported and fixed for fixed case. So there is a drastic change in the stress and displacement results. You can see there is a drastic change in the stress as well as the displacement results. The stress differs by a factor of 2. You see that the stress 76 becomes 38, almost half, right? The differs by the factor of 2. And displacement differs by the factor of 4. Here it's 0.64, here it's 0.16, almost 4 times less in case of fixed, and stress is 2 times less in case of fixed. Because of this one particular degree of freedom, that is the rotation about the z axis. That's free in case of simply supported and fixed for fixed condition. So now imagine the real life steel structure which is simply supported being modeled by a CA engineer as a fixed and analysis source results as a 200 Newton per ohm square, and displacement it shows 2.5 ohm. Since the magnitude of stress is less than real stress, it's less than 250. So we will understand like this is a wonderful PowerPoint and presentations of animation files will be submitted to design engineer. In conclusion, design is safe, but in real life, since it is a simply supported, magnitude of stress will be almost double. Instead of 200, it will become 400. In case real life structure that is simply supported, but in the FEM, CA has fixed as a fixed. Instead of simply supported, he has modeled as fixed because in real life it is simply supported situation. So what would happen? Your stress becomes almost 400 instead of the analysis shows 200, but in reality it will become 400. It's more than the yield value and it will become fail. The displacement also 4 times. That instead of 2.5 it become 10 hours. So structure will fail soon. So the real situation we need to consider while modeling it. CAE analysis in the FEM analysis. So boundary conditions is very important. And how to apply correct boundary condition? Who can teach us quickly? Application of boundary conditions is a tricky subject and is based purely on engineering judgment, skill, and common sense only. No university or consultant or book can teach these things. You have to understand this. This is something to be learned from practical and field experience, 100% involvement, thinking day and night about the behavior of the component due to various forces, checking after every iteration whether the FE model is behaving the same way as in reality. We need to understand that the FE model is behaving the same way in reality. Displacement plot, strain gauge results for static analysis, natural frequency response comparison for dynamic analysis has to be compared. If not, modifications to boundary conditions we need to see. Discussions with the CAE engineer and field engineer, testing department engineer in short, making mistakes and readiness to rework and modify the FE model again and again till satisfactory correlation is achieved is the feature. So experience is the true teacher as well as the common sense. We need to reflect the reality, especially for the boundary conditions. You can understand the importance of boundary conditions. In reality, if it is a simply supported, but in analysis, if we consider this as a fixed one, then analysis it will show only 200 as the stress, but in reality it will be 400 bending stress. 400 means it's more than yield value of 250, so it would fail in reality, but in analysis it will also pass. So we need to reflect the boundary condition. You see the boundary conditions, though it takes least time in the model, but it's most important stuff in FEA. Typically, brick missing 4-cylinder engine block requires 300 hours, but boundary condition requires 8 hours. So these 300 hours hard work could go in vain if boundary conditions are not applied properly. So the importance is we need to understand the significance of boundary condition. Boundary condition, it makes a lot of difference in the stress as well as displacement. One particular degrees of freedom is not restrained means it would have the stress almost 2 times compared to the fixed, right? That's what we have seen. So these particular degrees of freedom, that's free in case of simple supporter, but in case of fixed, it is not free, it is restrained. Almost like the fan also, it's limited between the point of counterflexure. Here, if you see the zero moment is from end to end, but in case of fixed, it will be the 0 moment it will be less, the span will be less. The distance between the 0 point moment will be less. Okay, it's almost 0.5 will go half of the span kind of